Welcome back. In this session, we discuss Rolle's theorem and two versions of mean value theorems. These theorems have many important consequences and applications. We begin with Rolle's theorem. Figure 1 shows the graph of a differentiable curve for which there is a horizontal line that crosses the curve at 2 points, a f of a and b f of b. Then it is obvious from the figure that there is a point c f of c on the curve where the tangent is horizontal, that is, the tangent is parallel to the x axis, and correspondingly slope of the tangent at that point is f dash c, that is equal to 0. In figure 2 also there is a horizontal line that crosses the curve at 2 points. For this curve, it can be seen that there are 3 points, C1 f of C1, C2 f of C2 and C3 f of C3, such that tangent at these points are horizontal, so that f dash C1 equal to 0, f dash C2 equal to 0 and f dash C3 equal to 0. The observations above are theoretically assured by a 300-year-old theorem of Michael Rolle, the French mathematician of 17th century. Now, we describe this theorem with its proof. Rolle's theorem. Suppose that y equal to f of x is continuous at every point of a closed interval a b and differentiable at every point of the open interval a b. If f of a equal to f of b, then there is at least one number c in open interval a b at which f dash c equal to 0. Now, we prove the theorem. As f is continuous, it assumes absolute maximum and minimum values on closed interval a b. As f dash x is at interior points, absolute maximum and minimum value of closed interval a b occur either at interior points where f dash is 0 or at a and b, the endpoints of the function's domain. If either the maximum or the minimum occur at an interior point c inside the interval, then f dash c equal to 0, and we have found such a point c that satisfies the Rolle's theorem. If both maximum and minimum are at a or b, various case arises. In any case, since f of a equal to f of b, it follows that maximum value of f of x over the interval a b is equal to minimum value of f of x over the interval a b. Thus, f is a constant function. Then obviously, the derivative f dash x equal to 0 for every x in the domain, and c can be any point in the interval open interval a b. This completes the proof. The Rolle's theorem has a nice algebraic interpretation. Let f of x be a polynomial function with f of a equal to f of b equal to 0, that is, a and b are roots of the polynomial f of x. Being a polynomial, f of x is continuous and differentiable at every real number. Hence, in particular, f of x is continuous on closed interval a b and differentiable in open interval a b. Thus, all the hypotheses of the Rolle's theorem are satisfied, and hence there is a root c in the open interval a b such that f dash c equal to 0. That is, there is a root c in the open interval a b for the derivative polynomial f dash x. As an example of the above algebraic interpretation, we consider the polynomial function f of x equal to x cube by 3 minus 3x, which is continuous at every point of the closed interval closed minus 3 and is differentiable at every point of the open interval open minus 3. Since f of minus 3 equal to 0 equal to f of 3, Rolle's theorem says that the derivative f dash must be 0 at least once in the open interval between a equal to minus 3 and b equal to 3. We examine this as follows. Let f dash x equal to x square minus 3 equal to 0 implies x plus root 3 into x minus root 3 equal to 0 implies x equal to minus root 3 and x equal to root 3. Both these points lies in the open interval open minus 3 3, that is f dash x equal to 0 twice in the open interval open minus 3 3. This verifies Rolle's theorem. As an illustration of Rolle's theorem, we consider the trigonometric function f of x equal to sin x that has two consecutive roots at x equal to 0 and x equal to 2 pi, that is f of 0 equal to sin 0 equal to 0 equal to sin 2 pi equal to f of 2 pi. Since f is continuous and differentiable everywhere, in particular it is continuous on closed interval 0 2 pi and differentiable in open interval 0 2 pi. Thus, Rolle's theorem guarantees that there is at least one number c in the interval open 0 2 pi such that f of c equal to 0. Since f dash x equal to cos x, we can find 2 points in the open interval open 0 2 pi, namely c equal to pi by 2 and c2 equal to 3 pi by 2, such that f dash c1 equal to 0 and f dash c2 equal to 0. As another example, we verify Rolle's theorem for the function f defined by f of x equal to x minus a raised to m into x minus b raised to n, where m and n are positive integers and x belongs to closed interval a b. Being a polynomial function in the variable x, the given function f of x is continuous and differentiable at every point in the real line, and hence in particular f is continuous on closed interval a b and differentiable on open interval a b. Also, f of a equal to 0 equal to f of b. Now, differentiating f with respect to x, we get f dash x equal to m into x minus a raised to m minus 1 into x minus b raised to n plus n into x minus a raised to m into x minus b raised to n minus 1, that is f dash x equals x minus a raised to m minus 1 into x minus b raised to n minus 1 whole into m into x minus b plus n into x minus a. Mark this equation number 1. Next, we verify whether there exists a point c f of c at which f dash c equal to 0. From equation 1, f dash x is equal to 0 implies x minus a raised to m minus 1 into x minus b raised to n minus 1 whole into m into x minus b plus n into x minus a equal to 0. This implies m into x minus b plus n into x minus a equal to 0. Since x minus a not equal to 0 and x minus b not equal to 0, as a less than x less than b, the above implies m plus n into x minus mb plus na equal to 0. This implies x equal to mb plus na whole divided by m plus n. Now, mb plus na divided by m plus n is a point within the interval a b dividing the interval in the ratio m is to n. Hence, if we take c equal to mb plus na divided by m plus n, we can conclude that there is a point c such that a less than c less than b, where f dash c equal to 0. Hence, Rolle's theorem is verified here. As another example, if f of x and g of x are continuous on closed interval 0 1 and differentiable on open interval 0 1, such that f of 0 equal to 2, g of 0 equal to 1, f of 1 equal to 6, g of 1 equal to 3. We show that there exists c satisfying 0 less than c less than 1 and f dash c equal to 2 times g dash of c. Consider the function phi of x equal to f of x minus 2 times g of x. Since f of x and g of x are continuous on closed interval 0 1, by difference rule of continuous functions, phi of x equal to f of x minus 2 times g of x is continuous on closed interval 0 1. Also, f of x and g of x are differentiable on open interval 0 1. So, by the difference rule of differentiation, phi of x is also differentiable in 0 less than x less than 1. Also, phi of 0 equal to f of 0 minus 2 times g of 0, that is obviously equal to 2 minus 2 equal to 0, and phi of 1 equal to f of 1 minus 2 times g of 1 equal to 6 minus 6, that is equal to 0. So, that phi of 0 equal to phi of 1 equal to 0. Hence, it follows that phi of x satisfies all the assumptions of Rolle's theorem. Therefore, by Rolle's theorem, there must exist at least one value of x, say c, that lies in open interval 0 1 such that phi dash c equal to 0, that is f dash c minus 2 times g dash of c equal to 0 or f dash c equal to 2 times g dash of c. One more example, we prove that if a naught, a 1, a 2 etc. a n are real numbers such that a naught by n plus 1 plus a 1 by n plus etc. plus a n minus 1 by 2 plus a n equal to 0, comma, there exists at least one number between 0 and 1 such that the polynomial a naught x raised to n plus a 1 x raised to n minus 1 plus a 2 x raised to n minus 2 plus etc. plus a n equal to 0. For this, we consider the function f defined by f of x equal to a naught by n plus 1 into x raised to n plus 1 plus a 1 by n into x raised to n plus etc. plus a n minus 1 by 2 into x square plus a n x with x in closed interval 0 1. Now, f being a polynomial, it satisfies the following conditions. First one, f is continuous in closed interval 0 1. Second one, f is differentiable in the open interval 0 1. Third one, substituting x equal to 0 in f of x, we obtain f of 0 equal to 0 and f of 1 equal to a naught by n plus 1 plus a 1 by n plus etc. plus a n minus 1 by 2 plus a n equal to 0 by assumption. Hence, the conditions of Rolle's theorem are satisfied. Thus, there exists some x in 0 1 such that f dash x equal to 0, that is a naught by n plus 1 into x raised to n plus a 1 by n into n x raised to n minus 1 plus etc. plus a n minus 1 by 2 into 2 x square plus a n equal to 0, that is a naught x raised to n plus a 1 x raised to n minus 1 plus a 2 x raised to n minus 2 plus etc. plus a n equal to 0. Next, we will discuss importance of the hypothesis of Rolle's theorem. We note that the hypothesis of Rolle's theorem are essential. If they fail at even one point, graph may not have the horizontal tangent. As an example, this is illustrated by considering the function f of x equal to tan x for the closed interval 0 pi. From the graph of f of x, it is clear that it has no horizontal tangent corresponding to any point in the interval closed to 0 pi, so that there is no c such that f dash c equal to 0. We cannot have the conclusion of the Rolle's theorem due to any one of the following reasons. Here, f of x equal to tan x is not defined at x equal to pi by 2. So, there is a discontinuity at x equal to pi by 2 to the function f of x equal to tan x. Also, f dash x equal to sec square x which does not exist at x equal to pi by 2. As another example, for the function f of x equal to x plus 1 for 2 less than or equal to x less than 8 and at 3 at x equal to 8. By looking at the graph of f of x, we can see that there is no c such that the tangent at the ordered pair c f of c is parallel to the x axis. That is, that there is no C such that f dash C equal to 0. We have f of 2 equal to 3 equal to f of 8, but the function is not continuous on the closed interval 2 8. Hence, one of the assumptions of Rolle's theorem does not hold, and hence the theorem cannot be applied to the function. As one more example, for the function g of x equal to x square for 0 less than or equal to x less than or equal to 3 equal to minus x plus 8 for 3 less than x less than or equal to 8. By looking at the graph of g of x, we can see that there is no C such that tangent at that ordered pair C g of C is parallel to the x axis. That is, there is no C such that g dash C equal to 0. Here g of 0 equal to g of 8, but the function is not continuous at the point x equal to 3 in the closed interval 0 8. Hence, one of the assumptions of Rolle's theorem does not hold, and hence the theorem cannot be applied to the function. As a final example in this regard, consider the function h of x equal to x square in the range closed interval 0 to minus x plus 6 for 2 less than x less than or equal to 6. By looking at the graph of h of x, we can see that there is no C such that tangent at C h of C is parallel to the x axis. That is, there is no C such that h dash of C equal to 0, even though h of 0 equal to h of 6 and the function is continuous on closed interval 0 6. It is not differentiable at the point x equal to 2 in the open interval open 0 6. Non differentiability of h at x equal to 2 can be observed from the graph, as there is a corner at the point 2 4. This can be justified by seeing that the left hand derivative at x equal to 2 is the derivative of x square, that is 2x, evaluated at x equal to 2, which is 4, while the right hand derivative at x equal to 2 is the derivative of minus x plus 6, that is minus 1, evaluated at x equal to 2, which is minus 1. As the left hand and right hand derivative are different, the function h is not differentiable at x equal to 2. Hence, one of the assumptions of Rolle's theorem does not hold, and hence the theorem cannot be applied to the function. Rolle's theorem is a special case of a non-general result called the mean value theorem. Theorem 2, Lagrange's mean value theorem. Suppose y equal to f of x be a function of x subject to the conditions. First one, f is continuous in the closed interval a b. Second one, f is differentiable in the open interval a b. Then there is a point C in the open interval a b at which f of b minus f of a by b minus a equal to f dash c. Marcus equation number 2. Remarks. The above theorem is known as Lagrange's mean value theorem in honor of Italian mathematician Joseph Louis Lagrange from 1736 to 1813. The mean value theorem in its modern form was later stated by the French mathematician Augustin Louis Cauchy from 1789 to 1857, and we will give the statement of the theorem before concluding this session. Rolle's theorem is a special case of mean value theorem with f of b equal to f of a equal to f of b. This is the case when values of the function f of x at the endpoints of the segment closed interval a b are equal. Now, f is continuous in the closed interval a b, f is differentiable in the open interval a b, and f of a equal to f of b. That implies by the mean value theorem that there is a point C in open interval a b such that f dash c equal to f of b minus f of a by b minus a equal to 0 by b minus a equal to 0. That is, we get Rolle's theorem as a special case of Lagrange mean value theorem. Geometrically, mean value theorem states that between any two points a f of a and b f of b on the graph of a differentiable function f, there is a point c such that a less than c less than b with the property that the tangent at c f of c to the graph of f is parallel to the chord joining a and b. In other words, the slope of the tangent at c f of c and slope of the chord AB are the same. As the slope of the chord AB is f of b minus f of a by b minus a, and slope of the tangent at c f of c is f dash c, it follows that f of b minus f of a by b minus a equal to f dash c. The mean value theorem has a clear physical interpretation too. If we assume that f of t represents the position of a body moving along a line depending on time t, then the ratio of f of b minus f of a by b minus a is the average velocity of the body in the period time b minus a. Since f dash t is the instantaneous velocity, this theorem means that there exists a moment of time c in which the instantaneous speed is equal to the average speed. Proof of the Lagrange's mean value theorem. To prove the theorem, we graph the function as a curve in the Cartesian plane and draw a line through the points a f of a and b f of b. Now, we find the equation of the line passing through a f of a and b f of b as follows. Since the slope of the line is f of b minus f of a by b minus a, if x g of x is an arbitrary point on the line, then we have a point slope equation of the line given by g of x equal to f of a plus f of b minus f of a by b minus a into x minus a. That is, the line is the graph of the function g of x equal to f of a plus f of b minus f of a by b minus a into x minus a. The vertical difference between the graph of f and the line g at x is h of x equal to f of x minus g of x. That is, h of x equal to f of x minus f of a minus f of b minus f of a by b minus a into x minus a. Mark as equation number 1. The function h is continuous on closed interval a b and differentiable on open interval a b because of both f and g are differentiable. Differentiating the equation 1 with respect to x, we obtain h dash of x equal to f dash x minus 0 minus f of b minus f of a by b minus a. Mark as equation number 2. Since the derivative of the constant function of the constant f of a is 0 and that of x minus a is 1. Also, as graph of f and g both pass through a f of a and b f of b, we have f of a equal to g of a and hence h of a equal to f of a minus g of a equal to 0. Similarly, h of b equal to f of b minus g of b equal to 0. So, h of a equal to h of b equal to 0. Hence, h satisfy the hypothesis of Rolle's theorem on closed interval a b. Therefore, h dash of c equal to 0 at some point c in a b. Hence, from equation number 2, 0 equal to f dash c minus f of b minus f of a by b minus a. This implies f dash c equal to f of b minus f of a by b minus a. This completes the proof of the Lagrange mean value theorem. As an example, the function f of x equal to x square is continuous for closed interval 0 to and differentiable in open interval 0 2. Since f of 0 equal to 0 and f of 2 equal to 4, the mean value theorem says that at some point c in the open interval 0 2, the derivative f dash x equal to 2x must have the value f dash c equal to 2c equal to f of 2 minus f of 0 by 2 minus 0, that is 2c equal to 4 minus 0 by 2 minus 0, that is c equal to 1. We verify Lagrange's mean value theorem for the function f of x equal to e raised to x on closed interval 0 1. Here f of x equal to e raised to x, since the exponential function is continuous at every point on the real line, in particular f is continuous in the closed interval 0 1. Also f dash x equal to e raised to x exists in the open interval 0 1. Hence, by Lagrange mean value theorem, we have f dash c equal to f of 1 minus f of 0 by 1 minus 0, that is e raised to c equal to e minus 1. By taking logarithm on both sides of the above equation, we obtain c equal to ln of e minus 1, which lies in the open interval 0 1. Hence, Lagrange mean value theorem is verified for the given function. We verify the mean value theorem and find c for f of x equal to x into x minus 1 into x minus 2 for a equal to 0 and b equal to 1 by 2. Being a polynomial, f of x is continuous for every value of x in the closed interval 0 1 by 2 and differentiable on open interval 0 1 by 2, with the derivative given by f dash x equal to 3x square minus 6x plus 2. Hence, by the mean value theorem, we have f dash c equal to f of 1 by 2 minus f of 0 by 1 by 2 minus 0, that is 3c square minus 6c plus 2 equal to 1 by 2 all cube minus 3 times 1 by 2 whole square plus 2 times 1 by 2 minus 0 minus f of a all divided by 1 by 2 minus 0. On simplification, that is equal to 3 by 4, that is 12c square minus 24c plus 5 equal to 0. Hence, c equal to 1.76 or 0.24, in which c equal to 0.24 belongs to open interval 0 1 by 2. Hence, the verification of the theorem. The required value of c is given by c equal to 0.24. Next is the physical interpretation of the mean value theorem. If we think of the number f of b minus f of a by b minus a as the average change in f over closed interval a b and f dash c as the instantaneous change, then the mean value theorem says that at some interior point the instantaneous change must equal the average change over the entire interval. As an example, if a car accelerating from 0 takes 8 seconds to go 120 meters, its average velocity for the 8-second interval is 120 minus 0 by 8 minus 0 equal to 120 by 8 equal to 15 meters per second equal to 54 kilometer per hour. At some point during the acceleration, mean value theorem says the speedometer must rate exactly 54 kilometers per hour. As another example, suppose a car is moving on a straight highway on which the speed limit is 80 kilometers per hour. At 10 am, a police car clocks the velocity of the car at 75 kilometers per hour, and at 10:10 am, a second police car posted 15 kilometers down the road clocks your velocity at 70 kilometers per hour. We are going to see that the police have a right to charge the driver of the car with a speeding violation. The distance covered by the car is 15 kilometers in 10 minutes, that is 15 kilometers in 1/6 hour. Hence, the average velocity of the car was f of b minus f of a by b minus a equal to displacement by time equal to 15 by 1/6 equal to 90 kilometers per hour. Hence, the mean value theorem guarantees the police that the instantaneous velocity of the car was 90 kilometers per hour at least once over the 15 kilometers section of the highway. We know that if a function f has a constant value on an interval I, then f is differentiable on I and f dash x equal to 0 for all x in I. We are going to show that converse of this statement is also true. That means, as a corollary of the Lagrange mean value theorem, we are going to show that functions with 0 derivatives are constant. That is, if f dash x equal to 0 at each point of the interval I, then f of x equal to c for all x in I, where c is a constant. We want to show that f has a constant value on I. We do so by showing that if x1 and x2 are any 2 points in I, then f of x1 equal to f of x2. Suppose that x1 and x2 are 2 points in I, numbered from left to right, so that x1 less than x2. Being differentiable on I, in particular f is differentiable at every point of closed interval x1 x2 and hence continues at every point as well. Therefore, f of x2 minus f of x1 by x2 minus x1 equal to f dash c for some point c in between x1 and x2. Since f dash equal to 0 throughout I, the above equation becomes f of x2 minus f of x1 by x2 minus x1 equal to 0, or f of x2 minus f of x1 equal to 0 implies f of x1 equal to f of x2. Since x1 and x2 are arbitrary points in I, this shows that f is a constant function on I. As an another application of the Lagrange mean value theorem, we are going to show that functions with the same derivative differ by a constant. That is, if f dash x equal to g dash of x at each point of the interval I, then there exists a constant c such that f of x equal to g of x plus c for all x in I. To prove this, we note that at each point x in I, the derivative of the difference between f and g, that is h equal to f minus g, is h dash of x equal to f dash x minus g dash x equal to 0. That is, we have h dash of x equal to 0 at each point of an interval I, then by the result above, h of x equal to c for all x in I, where c is a constant. That is, f of x minus g of x equal to c on I. So, f of x equal to g of x plus c. This completes the proof. The result above says that functions can have identical derivatives on an interval only if their values on the interval have a constant difference. We know, for instance, that the derivative of f of x equal to x square on the entire real line is 2x. Any other function with the derivative 2x on the entire real line must have the formula x square plus c for some value of c. We are now going to find the function f of x whose derivative is cos x and whose graph passes through the point ordered by pi 5. Since f of x has the same derivative as g of x equal to sin x, we know that f of x equal to sin x plus c for some constant c. The value of c can be determined from the condition that f of pi equal to 5, since the graph of f passes through the point pi 5. F of pi equal to sin pi plus c equal to 5, or c equal to 5. Thus, the formula for f is f of x equal to sin x plus 5. We conclude the session by stating Cauchy's version of the mean value theorem. Cauchy's mean value theorem: if two functions f of x and g of x are differentiable in a closed interval a b and g dash of x not equal to 0 for any value of x in closed interval a b, then there exists at least one value c of x belongs to the open interval a b such that f of b minus f of a by g of b minus g of a equal to f dash c by g dash of c. A natural question arises whether g of b minus g of a equal to 0 in the denominator of the above equation. That means g of b equal to g of a, which then by Rolle's theorem implies that there is a point d belongs to open a b such that g dash of d equal to 0, which is not possible, as by assumption g dash of x not equal to 0 for any value of x in closed interval a b. So, g of b minus g of a not equal to 0. Lagrange mean value theorem can be obtained as a special case of Cauchy's mean value theorem by taking g of x equal to x, then g of b minus g of a equal to b minus a, and g dash of x equal to d by dx of x equal to 1, and so in particular g dash of c equal to 1. Substituting these values in the equation, f of b minus f of a by g of b minus g of a equal to f dash c by g dash of c, we obtain f of b minus f of a by b minus a equal to f dash of c. Conclusion: in this session, we discussed Rolle's theorem, Lagrange's and Cauchy's mean value theorems. We have seen that Lagrange mean value theorem is a special case of Cauchy's mean value theorem, and Rolle's theorem is a special case of Lagrange mean value theorem. Many examples have been described to illustrate the theorems. Hope the session was useful for you. See you next time. Until then, goodbye.